Yeah, students, are you able to see the PPT? Students, are you able to see the PPT?
Yes, sir.
Yes, sir.
Okay,
Yes, sir.
right, right. So, okay, yesterday we started our discussion for Miller theorem, and here there is one figure, figure one. It is a two-port network with common impedance Z, right? So, uh, now this common impedance Z, this is connected to the input side at point A, right here, and at the output side at point B, right? So now we have to apply the Miller theorem so that we can break this impedance Z into two parts, right? Into two parts. One will be connected only at the input side and another will be connected only at the output side, right? So here, if we are seeing this circuit, uh, you can see it in this way. Uh, this is our two-port network, right? It can be a transistor or it can be JFET, whatever it may be, two-port network. Now here, these are the two ports, right? So suppose at the input side, we have the port 1 and 1 dash, right? So what we have done, here we have connected, suppose, one voltage source like this. This is Vs. This is the resistance of this voltage source. Okay. So through this one current will flow and we name it as Is. Right. This is our Is. Now uh, there will be some drop across this Rs. There will be some drop across this Rs. Now at this terminal 1 and 1 dash, here we have a voltage, we call it as Vi, input voltage, right, to this two-port network. Okay. Now to this two-port network, the current which will flow will be Is. Okay. Now you see the output section. Here we have two ports, two terminals, 2 and 2 dash, and suppose here we have connected one load resistor, RL, right? So this load resistor we have connected. So across this load resistor you will get a voltage V out. Same here you are getting this V out, right? So suppose here we have the current IL and here we have connected the impedance. one impedance is connected Z. Okay, this is B, this is A point. Now you see here IS current. Here we have current IS. Right? So this IS current is split at junction A in two parts. One is this is not. This is I input. Right? So at junction A, it is divided in two parts. One is I1 and another is going to this Z. And we call it as, suppose, I1. Right? So in this way, if you see the resistance here, right, at this point the resistance is Rs, which is equal to Vi by Is, and here you have resistance Ri, and this is equal to Vi by Ii, right? So in this way you visualize this circuit, right? So with this visualization, now what we will do, we will consider input side. Consider input side, right? And apply KCL, Kirchhoff's current law, at A, right? So here at point A, we will apply the Kirchhoff's current law. So you will find input current, sum of the input current is equal to sum of the output current. So input current is Is and output current is I and I1. So we have Is is equal to I plus I1, right? Now this Is, you see here, this section here. From here you can write the expression for Is, right? So it will be Vi by Rs. It is Vi by to II. So again you see the figure and you see this resistance. This resistance is Ri is equal to Vi by Ii. So from here you take the value of Ii. So it will be Vi divided by Ri. Vi divided by Ri. Okay. Plus. Now you just see, suppose this is one resistance. Okay. Some current is flowing through this. Let us assume it is I. Okay. Now its value is R, right? Now suppose this end is at potential V1, and this end is at potential V2, right? Then how we will write the expression for I? Yeah, somebody can tell me how we will write the expression for I?
V1 minus V2 by R.
V1 minus
Yeah,
V2
so it will be V1 minus V2 by R, right? In this way. So now you see this I1, right? Now I will open this figure. See this I1, right? So Z is one component, passive component. It can be a resistor. So if you want to write this current value I1, so the voltage at the end A minus voltage at the end B divide by resistance, that is your Z impedance, right? Okay. So now this A terminal is at potential Vi. B terminal is at potential Vo, output voltage, right? So in that term we can write this. So this Vi, basically Vi is your, V1 is your Vi and V2 is our Vo. In this way we can write this. So Vi minus Vo divide by Z. Okay. So this expression we have written from figure 1. By seeing the figure 1, we have written this expression, figure 1. Okay. Now what I will do, I will keep the left hand side same. I will not change it. Rs. This is equal to Vi by Ri plus. Now in the second expression, in the numerator, I will take Vi common. I will take Vi common, right? So in the bracket you will get 1 minus. Yes, what is the next term?
V0 by
V0 by Vi.
Yeah, it is V0 by Vi divided by Z. So Vi by Rs is equal to Vi by Ri plus Vi 1 minus. Now this V0,
Voltage gain.
yeah, since voltage gain is V0 by Vi, right? So this we will replace by voltage gain AB divided by Z. Now in the numerator, in all the three component, Vi is there, right? So we can remove this Vi because it is there in all the three components. So we can write it as 1 by Rs is equal to Vi by Ri plus 1 minus voltage gain divided by Z. Okay.
Sir, there 1 by Ri, no, sir.
1 by, yes, correct.
R.
Here. One by Ri, right? Now, suppose there are two resistors connected in parallel, right? There are two resistors connected in parallel. We call these resistors as R1 and R2. Okay. So, and suppose the uh, total resistance of this parallel combination, right? How we write that? We call it as R total. RT is the total resistance of this parallel combination, right? So uh, you, if you simplify, you find the value of RT, then you write in this way: 1 by RT is equal to 1 by
R1 R2 by R1 plus R2.
R1 plus 1 by R2, correct? 1 by
Yes, sir.
R2. Because if you simplify this, then you will get the value of RT as,
R1 R2 by R1 plus
yes, R1 R2 by R1 plus R2. R1 plus R2. Okay. Who is this student? Please mute, please. Okay. So now you see this expression. You see this expression, right? So here RS is equal to two resistors, or two resistors in parallel. And what are those resistors? See here, this, you see this expression 1 by RT is equal to 1 by R1 plus 1 by R2. This indicates that RT is equal to R1 in parallel with R2, right? Same way, if you see this expression, right? Then what are the two resistors which are in parallel? One is
Ri
R1,
and Z.
one is R1 and another is Ri in parallel with
Z.
Z. Y 1 minus AB. See, what is the dimension of AB, voltage gain? What is the unit of voltage gain?
No units.
It is having no unit, right? So this Z component, it will be of the unit of Z, correct? Because AV, you will get one dimensionless quantity. You subtract that from 1. Whatever you will get, you divide Z by that value. So you will get a value which is of the unit of Z, right? So see, if you write RS is equal to R1 parallel to Z by 1 minus AV, then you can write this expression in this way: 1 by RS is equal to 1 by Ri plus 1 by, yes, 1 by, what is the second component here? This part.
1 minus
Z by
Z by
1
1 minus X.
minus AB, right? So this you can write it as 1 by R1, sorry, Ri plus. In the denominator, you are having Z by 1 by 1, Z by 1 minus AB. So 1 minus AB will come in the numerator, right? Z. Z by this will be equivalent to this expression, right or wrong? This expression, you see, correct? So same expression is there. You see the last expression. What is the last expression? It is 1 by Rs is equal to 1 by Ri plus 1 minus Av by Z. So this indicates that Rs is equal to Ri plus, sorry, Ri in parallel with Z by 1 minus Av. Okay? Or I write it as Rs is equal to Ri in parallel with Z1, right? Here Z1 is equal to Z by 1 minus AB. Okay? So Z1 is called as Miller's input impedance, right? Z1 is Miller's input impedance, right? And simplified circuit at input side. It will be like this. Here we have Rs and here we have now Z1, right? So we have removed that Z which was connected at the input and output section, and in place of that we have connected one Miller input impedance Z1 whose value will be Z divided by 1 minus voltage gain, right? From that we will find the value of Z1 and we connect here, right? So now you see this is Z1 and the input impedance of this network is your Ri. So Rs is equal to parallel combination of this Z1 and Ri, right? Because this two-port network, you can replace this two-port network by its input resistance of Ri, right? And here you have one Z1. So here this Rs, it is parallel combination of Z1 and Ri. Now, if Z is capacitance, if Z is capacitance, right? Suppose Z is a resistor. So simply you can here you can replace this Z by a resistor. You connect one resistor, right? But suppose if Z is a capacitor, right? Then if Z is not capacitance, capacitive reactance, you can say. If Z is capacitive reactance, then we have written that since Z1 is equal to Z by 1 minus AB. So therefore you can express this Z1, we can write it as XC1 is equal to XC by 1 minus AB, right? So how we represent XC? XC is the capacitive reactance, and this 1 by, yes, tell 1 by
Rio में
2 pi f c, value of the capacitance, right? In this way we can represent this. So here XC1 is 1 by 2 pi f C1 is equal to 1 minus AB within bracket, and for XC also if you write in this term in this way, so it is 2 pi f c, right? 2 pi f and 2 pi f you can cancel out, so you will get 1 by C1 is equal to, see here it is 1 by C 1 minus AB, or C1 is equal to C 1 minus AB. This, okay? So here C1 is Miller's input capacitance. Right. So here, suppose if in this figure, if here we have C, one capacitor is connected here, right? Then what we can do, we can remove that capacitor, and in place of that capacitor we can connect one capacitor here with a value of C1, and the cells value C1 you can calculate by using this expression, right? The value of capacitor C multiplied by 1 minus voltage gain, right? In that way we can do the things, right? Now what we have done, at the input section we have connected now one impedance, that is Z1, right? And that is in parallel now. And if something is in parallel, whether it is resistance or capacitance, then you can calculate, you can analyze the things simply by using the parallel and series combination type of resistances or reactances, right? So now consider output side. Right? And apply Kirchhoff's current law at B. Now you apply Kirchhoff's current law at B. So now you see this figure at B, right? I write here figure 1. See this figure. So IL is equal to I2 plus I0, I2 plus I0. Right? Now what you do, how we solve the input side, exactly in the same way, you try to solve this expression, right? And then you find out the Miller output impedance and name it as Z2, right? And if Z is a capacitance, then you find out the Miller output capacitance, right? Reactance by using that. So exactly how we solve expression here, where we solve here, exactly in the same way you try to solve this now, right? In your copy you try to solve, then when I will solve, then you match it, whether it is coming or it is not coming. You try to solve this. Shall I keep the figure open or you remember that? Okay, I will open this figure, solve it. So you solve this in your copy and take the snapshot from your camera and me Yogesh dot m @ gmrit dot edu dot in. Okay, so I want to see how many students will do it and they will send me, right? You solve that part and send me the in your copy. You solve it and they take the photo of that, and that image you send me at this mail ID. Okay, right. Okay then.